All right, awesome. I get to tell you about Coco Values. So Coco stands for Cooperative Competitive Values.
Coco stands for that?
Well, the Coco part of Coco Values stands for Cooperative Competitive.
Okay.
And this is an idea due to Kalai and Kalai, because you need as many of those as you can get.
Mm-hmm.
Here is an example of Coco Values that features some people that you may recognize. So this is Curly and Smooth and the bananas. So Curly and Smooth would like to get bananas. Turns out Curly is too short to get any bananas.
So true.
And Smooth is tall enough to get 2 bananas.
Yeah, that's about right.
But if Smooth stood on top of Curly's head, then he could actually get 4 bananas. He could reach these 2 additional high bananas.
Oh, so it's like a Tuesday.
So let's set this up as a matrix game. Here's a matrix version of the game. So this is suggest to you, and you have 2 choices. You can just reach for the bananas yourself, or you could stand on top of my head and reach the other bananas.
So you're my friend in this.
Sorry, Curly. You could stand on top of Curly. Not you. I mean, Smooth can stand on top of Curly's head.
Okay.
And Curly has the choice of either allowing that to happen or not. Okay?
I like this game.
Yeah. Believe it or not, I did not make this up for the purposes of this class.
Uh-huh.
And so we can ask some questions about this. So, for example, what's the Nash?
Oh, I'm sorry. You're actually asking me what the Nash is? I guess
It's a rhetorical question, except it's not rhetorical. It's just a question.
Pure Nash?
If you can find one, sure.
Okay. Well, is there a pure Nash? I mean, I've just seen these numbers for the first time.
Yeah, but you shouldn't. Okay, sure.
So I can just ask the question. All right. So if we do don't boost and reach, would either want to move? Well, it doesn't really matter if you go from reach to climb. You get the same value.
Right.
And it doesn't matter if
you change. Sorry, you, right, you. Smooth. It doesn't matter to Smooth.
It doesn't matter to Smooth if you're in don't boost reach. And if you're in don't boost reach, it also doesn't, wait. No, I'm sorry. Take that back.
It does matter.
It does matter. I'm reading the numbers backwards. So the first one is for Curly, and the second number is for Smooth.
See, I put them in the same order as where they're standing.
No, and that makes perfect sense. So if you have 0, 2, so then if we're stuck on don't boost and Smooth can move from reach to climb, Smooth would not do that because you're going from 2 to 0.
Mm-hmm.
Meanwhile, if we're in don't boost reach and Curly can change, then Curly would go from 0 to 0. And that doesn't really make a difference. So I guess don't boost and reach is a Nash equilibrium. So let's see. I think there's a symmetry thing there. So we know don't boost and climb is not a Nash equilibrium.
Good.
For the same reason that 0, 2 is 1. 0, 0 is not, because I'd be going from 0 to 2 if I were Smooth. So there's no point worrying about that. What about boost and reach? Well, let's see. That's 0, 2. And so Curly doesn't need to move. It doesn't have an advantage to moving from boost to don't boost. But Smooth would want to move because you'd be going from 2 to 4. So that is not Nash equilibrium.
Okay.
Now let's look at boost and climb. So boost and climb, let's see, it's 0, 4. So if I went from boost to don't boost, I would still stay at 0. And so that doesn't help Curly any. And I wouldn't move from climb to reach because I'd be going from 4 to 2. And so therefore, that is also a Nash.
All right. Now, which Nash equilibrium do you think would be more beneficial?
Well, for Smooth, it would definitely be boost and climb.
Yeah. What about for, like, the society of these two people? Like, if you just add up the total retrieved bananas.
So that would be 2 versus 4.
Yeah.
So in fact, again, boost and climb would be, on average, more beneficial.
On average.
Or, the sum for the society.
Yeah.
Sum,
right.
average is all the same thing.
Right. But it sort of doesn't matter to Curly, but it would matter to Smooth. And it's also the case that to Nash, it doesn't really matter. Both of these are Nash equilibrium, so they're both perfectly acceptable from a Nash equilibrium sort of point of view.
Yeah, and this is like the example that I did with chicken, where you have 2 Nash equilibria, and they're both kind of equally good from Nash's point of view. Although in that case, they're very different from the 2 players' point of view. Here, I suppose, either way, Curly gets nothing. So really, it's just about making Smooth happy. I like this game.
So, okay, sure, fine. So that being said, can we say anything about correlated equilibria?
I mean, I'm sure we can, right? We can, any mixed Nash equilibria is a correlated equilibria, but I think this one's a little different right here, right? Because no matter what happens, Curly gets 0.
So that means that Curly, like anything's going to be equally okay to Curly.
Right.
So Curly's not really going to participate in the equilibriumness or lack thereof.
Right. So really, this is all about getting to boosting and climbing.
Yeah, though I think you said that any convex combination of a Nash is a correlated equilibrium.
That's right.
So it should be everything like 0, 2, 0, 2, 1, 0, 2, 2, 0, 2, 3, 0, 2, 4, 0, 2, 5, 0, 2, 6, all the way up to 0.03, 0.4. We know that all those have to be Nash.
Right.
Or values of correlated. There has to be a value of some correlated equilibrium that is like 0.3, for example.